In each of these cases, you want to create the graph first before you even get started. I recommend you do that on Desmos, right, just for convenience. So f of x would be equal to 1 over x minus 2. Now, my window is all out of whack, so I'm going to hit the home key or home icon to get a good looking graph right there. So what we're looking at is an equation that has a vertical asymptote at x equals 2. But if you're unsure about that, the location of the vertical asymptote, just take your denominator, the denominator of your fraction, set it equal to 0, and solve. And that'll give you your vertical asymptote. All right, so I'm actually just going to plot that real quick. So x equals 2. I'll make it look nice. All right. So when we're looking for a limit, what we're trying to identify is a y value that the graph is approaching as x gets closer and closer to a particular number. All right. So in this case, we're saying that x is getting closer and closer to the number 2 from the left. All right, so from the left. So start on the left side of the graph. All right, grab a point, start on the left side of the graph. Move that point closer and closer to the x value of 2. We're at 1, 1.5, 1 3/4. We're going, going, going. As we get closer and closer to the x value of 2, it seems to disappear off the screen on the low side. All right. If I continue going down, 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 you're going to see that it never stops going down. It'll get closer and closer to the x value of 2, but it'll never stop going down. A number that never stops going down or decreasing is also known as negative infinity. All right. So if I want to attack part B, it's saying x is approaching 2 from the right. Same idea. I'm going to grab a point on the right-hand side and start moving it towards the x value of 2. As I get closer and closer to the x value of 2, it seems to turn and start going upward off the grid. But if I continue scrolling up, you see that the curve never ends. It still gets closer and closer to the x value of 2, but it never stops increasing. A number that never stops increasing is known as positive infinity. All right. The last part, that's where this crazy notation gets in, or comes into play. It's kind of weird to look at if you're not overly familiar with it, but it's basically saying, is there an agreement or disagreement between the limit from the left-hand side and the limit from the right-hand side? All right. I call this the case of the missed high five. All right. If you're connecting with a high five, so the two sides of the limit, so coming in from the left, coming in from the right, they merge to the same location, then you would get the same answer for A and B. If they don't, then that's like two freshmen trying to give each other a high five in the hallway. It never really quite works out. All right, it's always like just a hideous miss. All right, if it's one of those situations, then it's a DNE. All right, does not exist. The limit does not exist. All right. So we're looking to see if there's an agreement from the left and from the right. If it does not agree, then it's DNE. I made that up myself. I just wish agree was spelled, E-G-R-E-E, but it's not. It doesn't quite work, but it gets there. All right. So then when you follow this same technique, looking at the next problem, x over x plus 3, we have an asymptote at x equals negative 3 this time. It's the same idea. Coming in from the left, we're going up forever. Infinity. Coming in from the right, we're going down forever. Negative infinity. They do not agree, so it's DNE. And I didn't actually draw any graphs. I mean, the graphs are here if you want to print it out and do it out, that's fine. But we're kind of living in Desmos land now. I mean, in a pre-calc class, or I guess gap 2.5 or whatever the last course is, you would have to probably draw the graphs, but we're beyond that now. All right, rough sketches are probably the most that we would ever need. All right, so there you go. You have a factorable denominator. So x minus 2, x plus 2. One of them is a common factor with the numerator. You see the x minus 2? That indicates the presence of a point discontinuity or a hole in the graph. Desmos is really helpful when it comes to this. X minus 2 over x squared minus 4. Pop it right in. I'll put my asymptote at -2. I know it's going to be at -2 because it looks like it's at -2. But even if I didn't, there's an algebraic way of figuring it out. All right. So what we would do is we take our denominators, set them equal to 0. You get x equals 2, x equals -2. Looking at the graph, we see a vertical asymptote at -2, so we're good there. I don't see an asymptote at +2. That means there must be a hole. Fortunately, Desmos will verify that for you. Just start scrolling or dragging along the curve. Once you get to 2, you'll see it'll actually make a hole on the graph temporarily at 2, whatever that undefined value is. So we know that there's a hole there. I just need to know what that location gives. So if I take my function and simplify it, x minus 2's will cancel out. That'll give me f of x is equal to 1 over x plus 2. What I'll do is I'll graph that also. I'll just put it in as y equals 1 over x plus 2. Oops. All right, you'll see that it actually maps to the same location. The exception is this one fills the hole. If I could get it to lock into place. So it's locking into place at 2, 1/4 or 0.25. That's because if I take this coordinate for the hole, or the x value, plug it in here, I'll get 1 over 2 plus 2, which is 1/4. All right, so when I go to create the graph, actually I'll just leave it on here. All I would have to do is just make sure I plot a hole at 2, 1/4. So long press on the point icon and make it an open circle, and you'll have the appropriate graph. So all of that is just so we can get to a point where we can answer the limit questions. So that actually makes this one of the more challenging types of questions. But once you do that, it's asking what's happening as you get closer and closer to 2 from the left. So if I'm following the path, I hop over the vertical asymptote and continue over here, I'm approaching the location of this open circle from the left. I'm approaching that same open circle from the right, both of which have coordinates, coordinates that involve y values of 0.25. All right, so the y value at that location is 0.25, no matter whether you come in from the left or the right. Since there's agreement there, that would be what your limit is. Right. No problem. I know it was a little